Welcome to the SAFECode e-learning course, Secure Java Programming 101. Secure coding in Java is a vast topic, and this 101 level course can only provide an introduction to it. The objective of the course is to show the most frequent attacks and pitfalls that a Java programmer may encounter, along with techniques to avoid them. The primary intended audiences for this course are architects, developers, and testers who are not familiar or maybe only slightly familiar with Java security. Development managers and people handling priorities and deferrals will also benefit from this material. There are three types of Java programs. There are standard stationary applications, web applications, and there's mobile code. Mobile code here does not refer to code used in mobile phones, but to the Java applets that are usually downloaded and run in different Java virtual machine form when they were initially stored. From a programmer's point of view, this makes for two distinct security scenarios. In the first case, which is stationary and web applications, all of your application is running in the Java virtual machine, or VM. In the case of mobile code, there can be many different applets, all downloaded from different sites, running simultaneously in the same Java VM. Obviously, it's important to isolate the different applets from each other, and Java has extensive features to do so. For example, security-managed class holders help isolate different code. The difference between these two scenarios is not necessarily always clear. Even when you wrote all the code running within a single Java VM, different objects may be acting on behalf of different users. For example, sending web requests from different clients. Or worse, objects may have been subverted by an attacker that provides the object with unexpected input. So to some extent, our Java code should always be cautious when dealing with the environment around it. It also makes for a much easier security code review, if the security of your code depends only on the object itself and not on other classes your object interacts with. In this course, we're not going to talk about mobile code and the security manager. We will focus exclusively on stationary code and web applications. But we will be cautious and consider that sometimes there may be a malicious Java object running in the same VM and trying to attack us. Java Enterprise Edition provides extensible authentication and authorization security primitives. We will not be talking about those in this course. These can be the topics of a different course in the future. We're also not going to talk about security-specific features such as digital signatures and encryption in detail. Java provides extensive crypto APIs, and this can also be the topic of a whole course by itself. Before we begin, I'd like to remind you about good coding practices that should be used in all programming languages. The first one is to validate all of your input. Insufficient input validation is probably the #1 cause of security vulnerabilities in web applications. Next on the list is least privilege. This practice helps us control how much damage can happen if something does go wrong. Unfortunately, our code can be put in unexpected conditions much more frequently than we'd hope. So judicious use of this principle can make for much more secure code. Software is most often used in its default state. Making sure this default is secure is a requirement much more than an option. Be sure to provide a safe default configuration and to always help your users along the path to security whenever they have to make a choice. Finally, it's a good idea to delegate security audit of code or solutions to experts who can focus exclusively on it. So whenever you can let experts do the work for you and use standard security frameworks that are provided for your technology, that is a good choice. To code securely, it's helpful to know what problems to avoid. Many of the security bugs that happen in Java also happen to other languages. But there are pitfalls that are unique to Java. Looking at the bright side first, Java's memory management avoids the most dangerous bugs found in C and C++ and other lower-level languages. Buffer overflows are simply not an issue in Java. Obviously, if you call non-Java applications from within Java, such as via the Java Native Interface or JNI, buffer overflows can be triggered in those non-Java applications. The Java virtual machine itself is not written in Java, and buffer overflows are found from time to time, so make sure to keep your Java VM installation up to date. Also, the worst integer wraparound and conversion problems are usually related to memory management as well. For example, when allocating space for a large array, having a negative number of elements may be a problem. Because Java does not deal with memory allocation, integer wraparound problems tend to be harder to exploit. Additionally, Java provides an extensive exception handling mechanism that allows you to easily handle unexpected conditions that are buried somewhere deep in the code. Unfortunately, we do not escape all evils, and the different kinds of injection attacks are just as easy to accomplish in Java as in many other languages. Java tends to be used very heavily for multi-threaded server-side code where multiple users can interact. Because of this usage, attackers can sometimes focus on problems with threading and synchronization to come up with denial-of-service attacks that cause servers to simply stop working. Finally, being an object-oriented language, Java has some objective semantic quirks that can cause unexpected results. We will see some of these later. Here's an outline of what we'll cover today. We'll start with three of the most common attacks: SQL injection, cross-site scripting, and cross-site request forgery, and their mitigation techniques. These are very important simply because they occur so often. We'll then look at Java object semantics and threading issues, followed by some common pitfalls that can occur when interfacing with other systems. The three kinds of attack we're going to talk about next are covered in detail in other SAFECode e-learning courses. These types of attacks are so prevalent that it is important to know how to avoid them while coding in Java. They have also caused so much pain that their solutions are now pre-packaged and readily available. Please refer to the corresponding courses for more details on these attacks. The first type of attack is SQL injection. Now, if you're not familiar with SQL injection, I'd advise you to first take our Injections 101 course. Like any other injection attack, SQL injection occurs when malicious user-provided input is not properly coerced into the format the programmer expected. For SQL injection, attackers escape the quoting of the SQL statement, usually by supplying an extra single quote followed by SQL code in an input field, such as is shown for the user ID here. The effects of SQL injection can be devastating. In the example shown here, SQL is used to compare the credentials of a user during the login to what is stored in the database. If a matching username and password are found, the user is logged in. By submitting characters that alter the logic of the SQL statement, an attacker can end the query and strip the part of the query where the password is checked. This is one example of how an attacker can use an SQL injection to break into an application. Java has an elegant, easy, and robust prepackaged solution against SQL injections: prepared statements. Unlike string concatenation, prepared statements work like a template and coerce each input parameter into a specific type. This prevents user input from escaping its quoting and being interpreted as part of the SQL statement itself, instead of just as an input parameter. Object relational mappers, ORMs, like the Hibernate framework, usually leverage the same protection mechanism. You have to make sure to use them right, however, as ORMs also provide a way to execute plain, unprotected SQL statements. Obviously, there are ways to misuse prepared statements by not using the type coercion mechanism. Also, sometimes simply enforcing type safety is not sufficient to provide a good overall solution. For example, an airline reservation system that uses prepared statements to specify dates may be immune to SQL injection, but it may still give end users the final price for flights that happened in the past, whereas the airline may not want to disclose that kind of information. So there are 2 points to remember here. Always coerce user-supplied input into the correct types before pushing them into a prepared statement. And always make sure that the business logic cannot be subverted by inputs that conform to those specified types. Let's now turn to cross-site scripting, also often referred to as XSS. This type of attack is also covered in depth in the XSS 101 course, and if you're not familiar with it, I suggest you take that course before proceeding with this one. The basic kind of XSS, which is also called reflected XSS, occurs when user input is displayed back to the same user, as shown in this simple example here. If that input is not validated before it is mirrored back within the web page, the attacker may be able to inject some JavaScript and have his malicious code execute within the context of the user's browser session. We can think of an XSS attack as a kind of injection attack. In the case of XSS, the attacker injects malicious JavaScript inside an HTML page. In SQL injection, the attacker injects a malicious SQL code snippet into the vulnerable SQL statement. Please note that this is a very brief discussion of XSS. There's a lot more information on the Open Web Application Security Project, OWASP website, and in the SAFECode XSS 101 course. There are two techniques that should be used to prevent XSS: input validation and output escaping. And let's talk about both of them. The first one, the input validation, is probably the most intuitive. The programmer simply has to make sure that the input is what you would expect it to be. Unfortunately, this is not as simple as it may seem. First, trying to specify everything that can go wrong is very hard to do. If we forget to specify some malicious input that the attacker may use, the malicious input will be allowed by default, and the attacker wins. So here's our first key point to remember about input validation. Use a positive specification, a so-called whitelist. Specify what should be in the input rather than what should not. Using a negative specification, in other words, a blacklist, well, that's bound to fail. The second problem is how to cope with input that does not fit the whitelist. If we try to sanitize the input, an attacker might try to trick our sanitization mechanism. Therefore, completely reject invalid input. Do not try to fix it. There are other problems with input validation. It can be impossible to implement simply because the programmer may not know in which context the input will later be used. Input validation doesn't help you if your database is already polluted with malicious input. Remember that it can be very hard to sanitize it. Because all of these pitfalls are hard to deal with, we strongly encourage you to always use input validation in conjunction with the next technique, output encoding. Output encoding is more robust than input validation. The reason is that at the time the data is going to be output, the context in which it will be shown to the user is precisely defined. So the programmer has all the information she needs. Output escaping usually involves HTML entity encoding, but depending on the context where the output will be placed, HTML, JavaScript, cascading style sheet, or URL encoding may be needed. HTML sanitization works similarly to output encoding, but allows you to whitelist specific HTML elements. There are several good prepackaged solutions for XSS shown at the bottom of the slide here. Your team may also have such a solution, or you may want to build upon these to develop your own. The solutions shown here all work like prepared statements. They are templating solutions. No matter which solution works best for you, always ensure that you consistently use it and make sure it always encodes for the correct context. There's a lot more detail and information on the OWASP website. The link on this slide is a great resource that's very interesting to read, and it can also be used for reference. We can now turn to Crosssite Request Forgery, or CSRF. Again, I suggest you take the SAFECode CSRF 101 course if you're not familiar with this attack. CSRF attacks occur because of the way browsers use cookies. If your web app is not using cookies for authentication, you're most likely not vulnerable to CSRF attacks. The CSRF attack pattern enables an attacker to gain remote control of someone else's browser. The slide shown illustrates the basic steps of the attack. First, the attacker must place some HTML on a carrier server. This can be a server he controls or some other server that allows the modification of its contents, such as a wiki or a bulletin board. The attacker must create the attack content in such a way that, when loaded in a browser, it will send requests to the target server. This can easily be done, for example, by setting the action the attacker wants to execute as the source of an image. Next, the attacker needs to lure potential victims to the malicious page. A successful attack requires that the victim opening the malicious web page is currently logged in to the target server. Otherwise, a forged request would be sent without a valid session cookie. Assume that the victim has initiated an authenticated session with the target server prior to loading the malicious web page. When processing the malicious web page, the browser automatically sends the forged request to the target server, for example, because it wants to load the image. If the forged requests fit into the current session context, the target server will accept and process them as intended by the attacker. Thus, the attacker achieves his goal and can make the victim execute commands without being aware of it, just by making the victim visit a seemingly harmless website. There are two possible solutions to CSRF attacks. The first possibility is to require re-authentication before critical actions. For example, before allowing transactions in an online banking application. Obviously, this cannot be done for all possible actions in our applications. The preferred solution is to insert a random number in all URLs that cause a state change in the server. The random number should be unpredictable and change with every user session. This is usually called a token or a nonce. A nonce is just a random number used only once. This nonce will be part of links for GET requests or hidden form fields for POST requests in the HTML content downloaded from the legitimate web application. Because the nonce is unpredictable and, unlike the cookie, is not automatically sent to the application, the attacker doesn't know what it is and becomes unable to craft the appropriate URLs when making his web requests. The unpredictability of the nonce means that the attacker is no longer able to perform the CSRF attack. And here is some good news. As you may expect, there are also robust prepackaged CSRF solutions for Java, and your team may also have its own solution. Whatever situation you find yourself in, do make sure that all HTTP requests that cause changes of state in the server have an appropriate CSRF prevention technique in place. Before we move on to the next group of problems, here are quick links to a few standard security frameworks for Java. These frameworks provide solutions to the three topics we've been discussing so far, as well as support for access control mechanisms. Now that we've dealt with the three worst offenders by using ready-made solutions, let's talk a little bit about Java goodness. Integer overflows are a serious problem in lower-level languages. This is not usually the case in Java. Integer overflows are very hard to exploit in Java because these calculations are not normally used to allocate memory. However, these bugs can still allow an attacker to force the system to mishandle other system resources, such as disk space or network connections. A very simple but also very common oversight is to forget to check the results of integer multiplication. Imagine that you're doing this very simple quantity times price calculation on the web shopping cart. Coming up with a negative value for the purchase may be all the attacker needs. One good rule of thumb to keep in mind is to avoid doing math on attacker-controlled inputs. It's usually best to do the same calculations on known predictable values. The two if statements in this slide are similar in intent, but the first does a little arithmetic on a value that can be controlled by the attacker, the length value, and it has an integer overflow problem, whereas the second does the math on known quantities, and that is safe. If avoiding doing math on attacker-controlled inputs, we have to do precondition checking or cast the type up to the next larger integer type. In the likely event that you have to deal with truly large numbers, the arbitrary precision big integer class can be used to avoid any overflow problem. On this slide, we've created a safe version of our shopping cart example from before, using upcasting. The attacker-provided quantity is upcasted to long before doing the multiplication with the unit price. This results in a long operation, which cannot overflow, using integer-type values as an input. The result can be outside the int range, however. In this case, the method throws an exception to inform the caller about the overflow. If the result is not overflowing, it is downcasted to int again and returned to the caller. In Java, the use of the equals equals operator in strings compares object references, not the content of the strings. When comparing two strings, the content is usually what you want to compare. Therefore, we should use the equals method call, not the equals equals operator. You may argue that the equals equals operator works. However, it only works because of a quirk in the current implementation of Java. The Java compiler coalesces all identical literal strings into a single memory location. This saves memory and also, as a side effect, makes the equals operator work many times, but not always. It is incorrect to use the equals equals operator in string comparisons for two reasons. First, although Sun's current implementation has this optimization, this is not required. A compliant Java implementation is not required to implement this optimization, and this is therefore non-compliant. In other words, brittle Java. Second, this does not work at all for comparisons of strings made on the fly. See the Java Language Specification, 3rd edition. The link is shown on the slide. The code shown here is an excerpt from the Java Language Specification. Take a good look at it. The equals equals comparison method outputs false in the condition above. This is clearly not what the programmer wants. If the programmer gets used to this bad practice, it will fail him or her in these dynamic cases. Also shown in the slide is an expression that always works for two strings, string 1 and string 2. Care must be taken for situations when either or both strings are null, and this expression does just that. Another gotcha to keep in mind is that unlike the string class, the equals method in the string buffer and string builder classes has not been overwritten, and therefore these classes are compared by reference, not value. Just like the object class, two string buffers will compare the same only if they are exactly the same object. Two different string buffer objects will always be different, independent of whether or not they contain the same string. If you need the more common compare by value behavior, you can call the toString method on both objects and then make the comparison using strings. Finally, here's a word of warning about declaring your arrays public and final. Because arrays are immutable objects, the final constraint requires that the array object itself be assigned to only once. However, it provides no guarantees about the array elements themselves. These can still change. Since the array is public, a malicious program can change the values stored in the array. Let's now consider a short list of coding problems that can lead to synchronization or denial of service attacks. The first three issues are quite straightforward and concern the finalize method. This method provides a means to reclaim non-Java resources, for example, files or socket connections. All objects that use external resources should provide a finalize method to clean up the resource. However, the finalize method will be called by the garbage collector when cleaning up, and therefore calling it yourself explicitly implies it will be called twice. We should also make sure that whenever we override the finalize method, we call the same method in the parent class, so that it too can clean up. Another simple pitfall that tends to be hard to find through testing occurs when programming in Java 2 Enterprise Edition. In this context, code running inside a container should never call system exit. This leads to shutting down the whole container, rather than just the multifunction part of the app, and could enable a denial of service attack. An explicit call to thread run is probably a mistake. This will not spawn a new thread, but rather run the code in the current one. You probably mean to call thread start instead. Thread start does spawn a new thread. There is a pernicious little synchronization issue we should consider. This occurs when multiple threads want access to multiple sources. We know from basic concurrent programming theory that whenever multiple locks have to be acquired by different threads, those locks should always be acquired in the same order. This prevents deadlocks, where one thread acquires a locked resource A and waits for another who's doing just the same thing, but locking resource B instead. Java synchronized methods and statements provide good synchronization primitives, but they can mask the fact that we are acquiring and releasing locks under the hood. And because of this kind of deadlock, we can have problems. Let's look at an example. Consider the code here. It intends to provide a thread-safe implementation of a hash set. In this piece of code, two locks are required. One lock is on the smart hash itself, and the other is on the mySet object. This code works well if the lock on the smart hash object is always acquired before the lock on the underlying hash set. However, consider this situation. A different programmer wanted to add some extra batch remove functionality. Because his operation may take a long time to complete, the programmer was extra cautious and synchronized on the mySet object. This is the mistake, and it can enable a denial of service attack. As you can see, the code no longer requires all the locks in the same order, and this code can deadlock in the line shown. Unfortunately, synchronization issues such as this one happen intermittently and are very hard to find in testing. If an attacker finds a condition like this in your code, he may be able to target it and bring your application to a halt. So be careful to make sure your code enters synchronized sections always in the same order. Even better, avoid synchronization where possible and use thread-safe classes. There are a number of problems that may not be Java's fault at all, but they can occur because of external code that is called via the Java native interface. As you can see in the example, where we are invoking a C function through the interface, even the standard buffer overflows can happen through this route. This vulnerability is better fixed in the C code than avoided in the JNI call. The common types of problems affecting the environment the Java application is running in are command injections and file path traversal. In both of these attacks, unvalidated parameters are passed to the underlying OS, as shown in the slide. Please see the Injections 101 course for more information on command injection. The file path traversal attacks allow the attacker to read or write to the directory location that he should not have access to. You should be very careful when unzipping compressed files, because the file paths specified in the compressed archive are relative to the current folder and can launch this type of attack. Please see the link at the bottom of this slide for more information. One data type that we need to pay close attention to when passing through the JNI or through the underlying OS is Unicode. Java's 16-bit presentation of characters can insert lots of dangerous 0 bytes in a string and cause problems if the callee is only expecting ASCII or characters encoded in UTF-8 instead of Java's UTF-16. Java was a leader in adopting multi-byte character sets, but its early implementation only allowed for 16 bits. The Unicode character set now allows 2 to the 31 possible characters, and Java has changed to accommodate that. The result is that we now have to know whether we use APIs that take characters encoded in UTF-16 or Unicode code points as ints. This also implies that even in Java, a character doesn't always have 16 bits. One further complication is that UTF-8 may need up to 6 bytes and not just 4 to present all 2 to the 31 possible Unicode characters. Most of these code points have not yet been assigned. All characters presently assigned fall into the UTF-8 4-byte range. But just like what happened to the 16 bits in Java, there's no guarantee this will remain the same in the future. When passing parameters across the JNI, it's better to be future-proof and safe. Java applications often use XML to store or transfer data. 2 attacks that can happen in Java concern XML Entity Expansion. The first external entity expansion, or XXE, is shown on the slide. The problem is that XML documents can specify system references to be included in the current document. Depending on how the parser has been implemented, this may or may not lead to lots of very interesting information being included in the document. In this example, Chapter 1 and Chapter 2 entities can contain lots of secret information. But more can be done. Chapter 3 can cause a denial of service attack on the parser if it decides to open the file in a Unix system. And Chapter 4 fetches malicious content from an attacker-controlled server. Unfortunately, many Java XML parsing methods can be subject to this attack, as they will happily comply with the standards and fetch those external entities. Parsing is hard. The safest way to avoid this is to not accept external document type definitions. Drop privileges in your parser so that your parser cannot get to any of those system references, even if it wants to. For most parsers, it's also possible to disable XML external entity to avoid this attack. As noted by Oracle's Secure Coding Guidelines, similar attacks that may use X include the XSLT document function and XSLT import and include elements. And this issue generally applies to the use of APIs that use XML but are not specifically XML APIs. For instance, Java Utils property load from XML does not itself have any protections from this attack. The second type of XML attacker that can cause us trouble is simple entity expansion, also called the billion laughs attack. This is a denial of service attack that causes an exponential blow-up in the resources needed by the parser, as seen in the example in the slide. This attack does not need access to any external sources. Simply complying with the standards and performing all the expressions is sufficient to cause a denial of service. Many parsers provide an option to limit the expansion to a reasonable amount. Ensure that the limitation is enabled for your application. Denial of service attacks tend to be more serious when attacking servers. Unfortunately, server-side code can also be harder to get right. Server-side development in Java usually uses frameworks that place more stringent requirements on the way your application code should behave. It is important to follow the guidelines specified by each framework. This slide shows some of the requirements that you must follow when using Enterprise Java Beans. Note that this is not an exhaustive list. As we noted before, the crypto APIs available in Java are quite extensive, and we're not going to talk about them in detail, except to make a couple of points. First, you should always assume that the latest and greatest crypto algorithms will eventually be broken. Write an application so that it can use improved algorithms in the future. We call this requirement crypto agility. The current suggested algorithms for symmetric and asymmetric encryption and cryptographic hashing are shown in the slide. When generating random numbers, avoid using random. Try to use secure random instead. Random is unsuitable for any security-related purposes, and sometimes the failure can be spectacular. Just to give you an example, the digital signature algorithm requires a random number as input. If that random number, that is only ever going to be used to sign a single document, can be predicted, it compromises the signer's private key and invalidates all documents ever signed with that key, not just the current one being signed. The link at the bottom provides more information on the Java Crypto API. Now let us summarize what we've learned today. Even though Java helps us to avoid mistakes like buffer overflows, secure coding in Java still is a vast topic. We briefly covered the most important aspects in a short time. But which Java attacks actually matter most for you depends on your applications. So make sure to analyze your apps using threat modeling techniques and deploy the protection mechanisms that really matter in your environment. Adhere to best practices and don't develop outside the Java specifications. For example, avoid using the reflection API. And to ensure that security vulnerabilities are avoided for your future developments, create and use coding guidelines. You'll find some good resources to start with on the next two slides. Also, use static code analyzers to find the bugs that still made it onto your application. The links here provide more information on secure coding guidelines for Java. Here are some more links with information on secure coding in Java. Thank you for taking this course.